I want to go back today and talk more about individual charges and the movement of individual charges. On Monday, we talked about objects being able to have a positive charge or a negative charge. We said a positively charged object resulted from having more protons than electrons, and negative was having more electrons than protons. So maybe you got a balloon that's negatively charged because it was rubbed against your hair. Well, if it became negatively charged because it was rubbed against your hair, it needed to receive electrons from your hair, and your hair needed to give away electrons. Your hair became positive, it became negative. How did it do that? What's the mechanism by which that charge was transferred? What's the mechanism by which we charge any object, let alone that balloon that was rubbed against your hair? Well, there's two mechanisms. The two general mechanisms or categories for charging objects we call conduction and induction. Conduction always involves a charge transfer. And remember, it's not protons that transfer. Protons are tightly bound in the nucleus. They're stuck where they are. If something's going to transfer, it's going to be electrons. So really what we mean here is that conduction always involves electron transfer. Electrons go from one object to the other or from the second back to the first. Electrons always move from one thing to the other in conduction. Induction never involves charge transfer. Never. Ask yourself, like, well, how do you have a charge if you're not transferring anything? How does the balloon become negative if you're not actually transferring charge to it? We'll deal with that in a second. Conduction usually involves, although not always, it usually involves touching. Two objects touching together. Whereas induction never involves touching. You're walking across the carpet in your living room. You're rubbing your feet along the carpet. You reach out your finger. You touch your little brother or sister in the finger. You give them a shock. You've just charged by conduction. Why? Because you transferred charge from you to him or her. You've also touched them. Okay? Conduction always involves a charge transfer, and it usually involves you physically, or whatever, physically touching the other object. Is there an example of conduction that involves charge transfer but doesn't involve touching? Yeah, there's lots of them. But there's less than involve touching. I'll give you one example of charging by conduction that doesn't involve touching. You've got a bunch of water molecules rubbing together. Okay? You develop a charge. Sometimes you get a pretty big buildup of charge in those water molecules. Clouds. Charge buildup. Earth is neutral. What happens sometimes? Electrons will discharge to the ground, or if the cloud becomes positive, the electrons will discharge up from the ground to the cloud. We get lightning, right? Are the cloud and the ground touching each other? No. Is it charging by conduction? Yeah, because it involved a transfer of charge. Didn't involve touching, but conduction doesn't have to involve touching. It just usually does. It has to involve a transfer of charge. Those electrons went from the cloud to the ground. It can't be induction because that never involves touching. It had to be conduction. Now we're going to break conduction up into two subcategories. One we call friction. We talked about the water droplets rubbing together and charging each other. That's charging by friction. When you walk across the carpet and you develop a charge, that's charging by friction. Okay? It's rubbing your feet against the carpet. It's rubbing the balloon against your hair. It's rubbing the water molecules against the water molecules. It's rubbing two things together, transferring electrons from one to the other. Now, the law of conservation of charge still holds here. If I've got a balloon and I've got hair, both of which are neutral, zero charge, and I rub them together and the balloon becomes -10, then what does my hair have to become? +10, because the total charge has to remain 0, right? When we rub things together, we can transfer electrons, not protons, but electrons from one to the other. That's charging by friction. Charging by contact, which sometimes, honestly, sometimes your exam doesn't even differentiate between these two subcategories. Sometimes it just calls charging by contact, charging by conduction, okay, the mother category, the overall category. Charging by contact involves usually touching two objects together. I'm going to put that in quotation marks because it doesn't always. Lightning is an example of charging by contact, even though the cloud and the ground never touch each other. They touch, or they come close enough for electrons to jump or to arc from one to the other. And then they try to balance out the charge. We've already talked about this a little bit, right? A couple days ago when we did the law of conservation of charge. One was neutral, one was -10. Touch them together, they become -5 and -5. That's charging by contact, charging by conduction. Now, charging by induction, a little bit different, because we don't actually physically touch or we don't actually physically transfer charge here from one to the other. Let's talk about the first subcategory first, and that's the temporary separation of charge that can be induced here. Got a picture. We got 4 positives evenly distributed around. Maybe we got 4 million positives. Maybe we got 132,612 positives. Doesn't matter. We have an equal number of negatives. Whatever it is, we have an equal number of negatives. And they're pretty much randomly distributed as well. Let's bring, Zach, let's bring a negatively charged object nearby. I'm drawing a whole bunch of negatives on there. It doesn't mean it's just negatives, but easier to draw it that way. There's positives as well. It's just more negatives than positives. Answer this question for me, please. What's going to happen to those protons in the neutral object? Where are they going to go? Let's assume this is a solid. Okay, it's not a liquid, it's not a gas, it's a solid. What's going to happen to those protons, those positive charges there? Where are they going to go? It's a trick question. Where are the protons located in the atom? Good. Where can they go? Nowhere. They stay where they are. They want to go somewhere. They want to be attracted to this negatively charged object, right? The positives want to be pulled over towards it, but they can't. They're stuck in the nucleus. It's like they're in jail, the nucleus jail. They can't go anywhere. They want to go over there. They can't. They see freedom over here. They want to go towards freedom, but they can't because they're stuck in there. What about the negatives, though? Where do they go? Where do they go, Alex? Good. They're repelled by the negative object. So instead of sticking around where they are here, they're going to go over here. Now, I'm simplifying this a little bit. You're not going to get every electron in this neutral object going to the left side. Some of them are going to stay where they are. But you'll get enough to go to the left side that you end up with what we call a separation of charge. This side is negative because it's got more negatives than positives. This side is positive because it's got more positives than negatives. It's a separation of charge. Why do you think we call it temporary, though? What's temporary about it? Why isn't it permanent? Yeah, Kathleen? Good. When the negative rectangle thing goes away, they go back to where they were before. The electrons get distributed all over the place again, and it becomes, well, it's still neutral. I was going to say it becomes neutral. It's still neutral. But we know we lose that separation of charge because they become evenly distributed. All right, we'll deal with how we can make it permanent in a moment here. Let's draw another picture, though, first. This time, let's draw an object that is neutral again. But beside that neutral object, with 4 positives and 4 negatives, beside that neutral object is, this time, a positively charged object. Whole bunch of protons, whole bunch of electrons as well, but more protons than electrons. What's going to happen, Derek, what's going to happen to the protons in that neutral object? Nope. Justin, what's going to happen to the protons? What's going to happen to the protons, Victoria? Yeah, they just stay where they are. Protons can't go anywhere, right? Good question. They got to stay where they are because they're in that nucleus, tightly bound. What's going to happen to the electrons in there? Alex? Good. They're going to be pulled over here to the right. They're going to be attracted to this positively charged object. They stay in there. So it's still a neutral object. But now we have one side that's positive and one side that's negative. I want you to take special note of this. The side of the object that's being charged, right? The side of a neutral object that's closest to the charging object, notice is opposite. This is positive, this is negative. This is negative, this is positive. That's always going to happen. Remember we said on Monday, charged objects attract neutral objects? This is why. Charged objects attract neutral objects because you induce a temporary separation of charge, and because, fundamentally, positive and negative attract each other, because opposites attract. You can't get a proton attracting a neutron because you can't get a separation of charge in a neutron. You have to be able to have a temporary separation of charge for positive to attract neutral. Does that make sense? So the answer to the question is temporary separation of charge, charged objects, temporary separation of charge, positive attracts negative. The question is, could be any one of a number of things. Basically, it's why do charged objects attract neutral objects? Maybe it's why does your comb, after you've rubbed your hair with it, attract little pieces of paper? Maybe it's why does the balloon that's charged attached to the wall be attracted to the wall? Doesn't matter. Okay? The answer is induction, temporary separation of charge, opposites attract. All right. Finally, one more little thing, and then we're going to shut it down for the day. How do we make it permanent? Okay, this is temporary because, as we know, Kathleen told us a minute ago, if we take that green rectangle thing away, then the charges are going back to where they were, right? So how do we make it permanent? You ever heard of a term called grounding? A grounding wire, or something is grounded? Yes? A grounding wire, or when something is grounded, it just simply means that the object is electrically connected to the earth, or something big like the earth. It doesn't have to be the earth. You could ground something on Mars too. You could ground something with a really, really big object on Earth. Okay, but it's attached to the earth or something like the earth. That's it. It's just an electrical connection, we'll say, to the earth. Here's the symbol for a grounding wire. It could be literally a wire. It could be you. You can ground something, right? You can provide an electrical path to the earth. If you've got a massive buildup of charge on you, and you're standing up on a wooden stool, and I go and touch you, then I provide an electrical connection to the earth. I've grounded you. What happens to these protons in the first diagram if there's a grounding wire there? Derek? They stay where they are. Good. You pass. What happens to the protons in the second case? Down here, the second diagram, if there's a grounding wire attached, Derek? They stay where they are. Good. What happens to the electrons in the first case? Chelsea, what happens to the electrons right here, do you think? What happened when the grounding wire wasn't there? They were pushed to the left side. Now we have an electrical connection to the ground. No? because that would be attracted to the negatives, right? That's not going to happen. They're pushed away. They're pushed away by this negative. Sorry? They're going to what, sorry? Back to where they were? No. No. Here's, you know what, I'm glad you said that, though. I'm glad both of you guys said that. Remember what we said, one of the things that we always have to have in the back of our minds is, why? Okay, so somebody's saying here, oh, they're going to go back to where they were. Why? Why would they go back to where they were? You got a grounding wire. Why does that put them back to where they were? Is there some kind of mysterious force pushing them back to where they were? No. These electrons want to be repelled by electrons. They stopped at the edge of the neutral object, right? But once you attach a grounding wire there, why would they stop? If there's an electrical connection there, why wouldn't they just keep going? They do. The electrons, these electrons get pushed down into the ground like that. That only works if you have an electrical connection, a conductor going into the ground. It's still not it's still not permanent though. If we take this thing away, if we take this away, these electrons are just going to go right back up and take the place of where they came from. Why? Because that would be positive, and it would suck up electrons from the neutral ground to the positive object in an attempt to balance them out. We'd never balance it out, right? Because you could never balance it out with the Earth, but it would try. It would suck those negatives back. So how do you make it permanent? We're almost there. How do you make it permanent? So that you can take this thing away and keep this positive. Cut the ground wire or remove the ground wire. Electrons want to go back up and take its place, but they can't because there's no connection now. What would happen here? Well, this time electrons get sucked up from the ground. Right? This side is positive. It sucks the electrons up, attracts the electrons. Get a whole bunch of extra electrons in here. Now you cut the ground wire, and look at this. This one's positively charged permanent, and this one's negatively charged permanent.